Example 3 says, solve the initial value problem. Y prime equals 2 times 1 plus x times 1 plus y squared. And the initial condition is y of 0 equals 0. And once we find the solution to what y is, we want to find where that function has a minimum value. So to start with, we can easily see that this is separable by dividing by 1 plus y squared. So what we'll have, thinking of our y prime as dy dx, if I divide by 1 plus y squared on the left, I'll have 1 over 1 plus y squared. That'll be dy. Cross multiplying by dx, I'll get, and I'm going to distribute through by this 2 here into the parentheses. So we'll get 2 plus 2x, and that's going to be a dx. And then integrate each side, on the left with respect to y and on the right with respect to x. And the antiderivative on the left, you should recognize that as the arctangent of y, equals, on the right, I'll get 2x plus x squared plus a constant. We need to find out what that constant is, and now's a good time to use our initial condition of y of 0 is 0 and substitute that back in. So that's going to give me the arctangent of 0 equals, let's see, when x is 0, I'll get a 0 plus our constant. And the arctangent of 0 is 0, which means that is my constant. Haha, so constant is 0. That gives me the arctangent of y now is equal to just the 2x plus x squared, or we can write that as x squared plus 2x. So coming up here, what it looks like we have, let's see, solving for y, let's take the tangent of each side. So y is equal to the tangent of 2x plus x squared. There. And there is the solution to our initial value problem. And what we want to do is figure out where that function has a minimum value. So from calculus, we know to find the minimum value or a maximum value, we need to find the derivative of y. So find the derivative of tangent of 2x plus x squared, set it equal to 0, find our critical numbers, and then find the value. But I don't need to take the derivative of this function to find when y prime is equal to 0. I already have what y prime is equal to right here. I just need to set this equal to 0 and find out where that occurs. So let me take 0, which is equal to now 2 times 1 plus x times 1 plus y squared. This obviously is never equal to 0. The only place this is going to be 0 is right here when 1 plus x is 0, or we can see that's going to occur when x is negative 1. So there's our critical value, which means we'll have either a max or a min, or potentially a saddle point when we evaluate our function y at negative 1, which will be the tangent of 2 times negative 1 plus negative 1 squared. So it looks like I have here negative 2 plus 1 is negative 1. So it looks like the tangent of negative 1 is going to be our max or min, and we'll show that it actually is a minimum value. And that minimum value looks like it occurs when x is 1 and y is the tangent of 1. So we could throw the second derivative test at our function and try to find out if it's a max or a min, but I really don't have my first derivative in terms of x by itself. I didn't take the derivative of this function. So instead, let's graph the function and see if it does look like there's a minimum value at this negative 1 tangent. Oops, that's supposed to be the tangent of negative 1 there. So Sage Math is actually up and running, so I'm going to solve it on Sage Math. So we want to plot our solution. So I'm going to plot. Our solution was the tangent of 2x plus x squared. And I'm going to plot it for x's between, let's go from, I don't know, minus let's go from -3 to 1 there to see what we end up getting. So start out with just the simple expression to plot. See what I get. And I get an, oops, that's right, I need to make this 2 times x so it knows what it is. And, ooh, ugly graph. So obviously we've got some asymptotes going on in here. The y-scale is way off. So let's shrink down the y's a little bit. I want the y min to be, let's say, -3, and the y max to equal +3. Let's see how that looks. Aha, much better. And it certainly does appear that we've got a minimum value when x is -1. So I'm going to try to plot this graph along with a point to see if it really works out. So I'm going to let p1 equal the graph of that function. And then to that p1, I'm going to add, with a plus equals, that's going to add another graphic to p1. I'm going to graph a point that is at -1, what was it, the tangent of -1, and I'm going to make my point size to be, I don't know, 30 pixels maybe, 20 pixels, and let's make the color of it equal red so we can see it maybe a little bit better. So let's, and then I'm going to have to show what that looks like. So I'm going to do show the graphic P1, and hopefully we get a red point at the very minimum of that function. And there it is. There we have a little tiny minimum right at -1, tangent of -1, and we've solved our problem.